Okay, so for this module, we're going over an introduction, or at least the beginning of some data management. So now we've gone through the intro to R, intro to R Markdown, hopefully, and some of the dplyr functions with the tidyverse to get us really into what the tidyverse is, as well as what's going on. So for this module, we'll discuss some of the common useful data tidying functions in the tidyr package, which is still part of that tidyverse suite of packages. And then we can also combine these functions with the dplyr packages or dplyr functions we've been working with, such as like filter, arrange, mutate, group by, summarize, that kind of stuff. So today, load the tidyverse package as well as the fish data. And again, this is the same data we have been working with. It's the long-term resource monitoring element of the Upper Mississippi River Restoration Program, and it's a select data from 2018 for 6 of the different species. This is 6 different sites on the Mississippi River. So it's community data of these 6 species, and we can do a lot with this to tidy it up and make this very unwieldy data set of 86 columns and 4,809 rows much more manageable. So one of the things that's really crucial to talk about are missing data. So often there's missing data within data sets, and we might not even realize it when we get the data. So often when we know there's missing data, there are NAs. Those data are explicitly missing. So they're NAs such or negative 9999 or a period or something. They're just missing out of that data set. Those are what are called explicit missing values. They're explicitly written there. On the other hand, there's implicit missing values, and these are ones that are completely missing from the data set. So there's no NAs, there's no rows, there's no columns for them. Either these data were just missing or they weren't gathered. So explicit missing values are much more obvious because they have that value there, while those implicit missing values are very important as well, but they can be easily overlooked. So this might be something if you were collecting organisms in the wild or in stomach contents maybe, and you didn't find certain species within that stomach or during your sampling event in nature, and so you just didn't record them. When in reality, those are zeros. You don't have an abundance for them in that stomach or during that sampling event. So you can input those zeros in R pretty easily. This is really important with fisheries data where you have catches and you're trying to look at like average catch across some sort of net or sampling event. And there's missing zeros for those different fish. You can easily input them. You do not have to do this by hand, which I think some people still do, unfortunately. So we're going to start off with the easy thing about explicit missing data with NAs or what other character string you want to put in for NA. So you can, if these data are explicitly missing and there's NAs or some other value for them, you can easily change what those explicit data are or easily filter them out or add them in. So you can replace specific values in data sets with NAs and vice versa. So we previously did this in one of the other modules to show a couple methods for removing NAs from functions, like na.rm equals true, or is.na and your variable. But there are also a couple other ways to remove NA in an object permanently for the R session or to save your data that way. So these are a couple ways we did this previously to remove NAs within our specific functions. Within filter, specify your data set, and we want to say we don't want to include any rows where the NA value or there is an NA value in the weight column. So if we do this, that removes like 1,400 fish because it was about 4,800. Now it's 3,484. So it's a lot of fish that were removed that did not have weight values there, but that is one way to remove it. for that data set in this function specifically. You can, when you are summarizing data, if you do not remove NAs, it will give you an error for a lot of functions like mean and those types of things, or sum or anything like that. So when you're using like summarize as a function, for example, we want to say, look in our fish data set, summarize the mean total length across all these fish. So mean of length, and then we also want mean weight, because weight we know has like 1,500 plus NA values in it. If we don't remove those NA values, then it'll give us an error or negative infinity for the mean. So we'll need to remove them. And one way to do that is just like we did here, the exclamation point, which means not, is dot NA means is it in NA, is it missing data? And then our column. So if we do this, we have a mean total length and a mean weight. If we did not remove NAs, it gives us an NA there because it can't calculate the mean when a bunch of missing values are present. The other way to do this for summarize or other functions here is down here with the na.rm equals true. So we'll look at that in a moment. It's the same thing as removing it this way. It's just a different way of writing it. So yeah, let's look at this catfish example. So if we filter for catfish, and then let's say, oh, we want to mutate the percent weight that each individual catfish comprises out of the entire catfish group or species. When we sum, we have to remove those NAs of weight because otherwise it's going to give us an NA for the sum or a weird value. It just can't calculate that. So we have to say, comma, na.rm equals true, which is the same exact thing as exclamation point is dot na weight. Those are interchangeable, so feel free to use either one, whichever one makes the most sense. Either exclamation point is dot na in your column or the function, your column, and then comma na.rm equals true. Same thing. So those are things that we've talked about before. Here's a new one, or sorry, this isn't a new one. In an entire data set, you can remove NAs. So this is just based on one column specifically. So we're removing the NAs from the weight column. In an entire data set, we can remove them as well. So let's say we want to remove all the NAs from our fish data set. So we filter within the entire data set and save it is.na weight. So we are doing it here in just one function for one variable, which is great. That helps us. But if we wanted to just remove it from our data set, we have to save over that data set or save it as a new object that does not have those NAs in it. And then we can use that object for analysis as well. This is a new function now. So you can replace NAs with a specified value or vice versa. So what if you wanted to make all NAs 0 for some reason, or that they actually did mean 0, like 0 catches? So this is our original data for weight. Lots of NAs in here. Many, many, many NAs. Maybe we want to say, okay, let's take the weight column here of the fish data set and we want to make it a new column, so mutate, and we have this column named weight 2, and we're going to use this function replace NA. So this is replacing every single NA in that column with a new value. So maybe with say which column it is, weight column, and then whatever you want to replace those NAs with. So maybe the NA, the missing weights are 1 or 0 weight or something. So maybe 1 weight, 1 gram or something like that. And then we're just going to select the 2 weight columns just so it's easier to see and then look at the some of the rows using slice to compare the NA changes. So this is just to show what it actually did in the data. This is the actual function we want. So the original data had all NAs for these rows here, 61 through 70. And the data we just made, the weight 2 column here, replaced all those NAs with 1 because that's what we told it to do. Replace underscore NA in the weight column, make them 1. So that's exactly what we told it to do, just to show that it does replace those NAs there. So that's a really easy way to replace a bunch of NAs in a singular column. You could also change this code to be multiple columns if you wanted. So you can also replace specific cell values with NAs. For example, if missing values are denoted as X, blanks, -999, whatever you have, you can convert those cell contents to NAs to make them explicit and more uniform across multiple data sets. So let's take our weight 2 column and say this is the weight column we just made here, and all of our ones are NAs. So we're just taking that column again right here, just those ones, and say NA underscore if. Take our weight 2 column, so the same column, we're just writing over it. And since we changed that from 0 to 1 in the last function, we'll just change this to 1 here. So this is saying replace, make it NA if that value is 1. So whatever your value is for NA, put that there. So right now we have 1 here. What this does for us is it just changes it back to NA. We're just changing the data to show what it's actually doing. This is much more functional if you have actual NAs in your data that you are trying to change, not just switch back and forth. So this is just for show right now. But if you have -999 or whatever, just put that in there. You could have blanks. You could do like whatever here, a blank there, anything like that, to show those are what you are replacing with NAs. As a very important note, please think carefully about what an NA means in your data set and how that's going to influence your future calculations or statistical analyses before you remove them or transform your data into a different value. So here I'm just showing you how to replace those NAs, how to change different values to NAs, but like just stop and think about what do those NAs mean? Are they missing data? Are they just really low numbers? What is that going to do to your data set? Like, is it going to change their sample size if you remove those? Or uh, is it adding in variation or something? So just think about it. Do you want to remove them? Do you want to change them? Move from there. Okay, so those are explicit missing values. And now we're going to talk about implicit missing data to make it explicit with the complete function. So sometimes we have those implicit missing data if those data were like never collected, so you only sample some months and not others, for example, or you don't record zeros for catches in a net. And these missing values are not readily obvious because they're not in the data set again, but it is important to consider when doing many analyses or visualizations. Like you still need to include zero catches. You should, depending on what your spatial or temporal scope is, you might have to include zeros or missing data for other months or something like that. So as an example, what if we wanted to look at catches of all species across each site in this data set, including when no fish, so 0 fish, were caught at a site? For this data set, there were no 0 catches recorded. So we would need to make this implicit missing data explicit. And then to make the data explicit, we need to determine which variables are associated with your level of comparison. So like, are you looking across sites, across nets, across gear types, individual IDs? Like what level of comparison are you doing and how explicit do you need to get with these missing values? So within this data set, L code is the site code. And this is the variable that distinguishes all sites from one another, which is the level at which catches happen. So if we're using this site code as our level to look at for comparison for including those zero catches, that's what we need to incorporate in this function. So we're going to save a new data set called fish2 from our fish data set. So the original one, we're using this function complete. At the beginning, you include which columns you are completing by. So our site code, L code, is one we have to complete by. And what we want to complete are for zero catches of each species. So we also have to include the species variable here. So this is basically like grouping by your data to fill in zeros or to fill in whatever number you have. So group by here site and species, L code and species. And we say fill equals, always put a list here. You can change whichever values you want. You can make multiple values in here. You can play around with this function. And we're saying fill in the catch variable with 0. So there is a variable in here called catch, and it's 1 for every single cell in here because they're individual fish. But we want to make sure that for each site, we are including 0 catches as well. So we need to include that 0. So name your data set if you need it, which we have up here. Specify which data columns you are trying to complete by, which is site and species for us, and then fill in whatever columns you need with whichever data. So if we had to fill in multiple other columns, list here, maybe we need to fill in date with some sort of value. We could say like NA or something like that. But that is how you would include more stuff in that list there. But we just want to fill in the catch here. So what this looks like now is we go down to catch, which is right here. We have zeros included as well now. They used to all just be ones, but now we have zeros because some of the combinations of species at each site were not counted before. They were not collected, they were not caught, so they were not in the data set. And now they are. We now have the catches of 0 fish per site explicitly stated in this data set. So if we look at this data set, we have 5,583 rows instead of the 4,800. So that added a lot more rows, over 700 of them, where we now have zeros for that. If we look at the data where the new explicit missing values are, we can see that the columns throughout the data set are NA rather than filled in with the data like the sampling date, the codes, or the site code, etc. So if we look at that a moment, the first 2 rows were where we filled in with zeros. We just have NAs for all of these columns besides L code and species because we asked it to fill in those. So literally just everything is NA for those columns. We probably don't want that. We likely want all the other information like the sampling date, the vegetation type for that site, the bottom type, the DO, the temperature, all that information we still want for that site. It won't fill it in just using complete. What we have to do is fill in the missing data with this fill argument. So we're going to create a new object just so we can see what's going on. from the data set we just made where we completed the data for zeros. First, we are going to arrange by L code and bar code. So L code again is the site data. So we still want to fill in by each site. So I would put that first, fill in or arrange your data by whatever you completed your data with, which was L code or the site code. So that's the first one here. And then we need some sort of unique identifier for each individual catch. For this, we for the catches we had species as that individual identifier, which is filled in for all of them. So we need something that also IDs these species, which for this data set is a barcode. It's a unique individual identifier. So what this does so far is it arranges our data. So our first two rows are no longer the NAs all the way across those rows. That's what we're trying to do is avoid NAs all the way across those rows because with fill, this fill function, we have to fill in from either top down or bottom up. And from top down, we have to have these variables, these rows filled in, and we want them to be filling in by the site, the date, etc., that they are associated with for those missing values in all those rows. So if we look at our fish2 data set, we have the NAs up front, and then we try to arrange it so those NAs are not up front because this fill is going to fill in this data set from the down to the down direction. So from top up here down. So that's why we have to arrange it. And what this fill does is it takes whatever columns you want, and it's just going to fill in all of those NA values across those rows. And we just have to make sure that those rows are lining up with that site-specific information that we filled in by. And that is how we do the arrange. So make sure to arrange by the variable you completed, and then some sort of identifying variable or however you can get it. So you are filling from either bottom up or top down. So this fill function specify which columns you want to fill. So we're trying to fill in site here through grep width, which will be way towards the back. So we're not including all of these. We're not including things like weight, catch here, all this other information, which is just NAs to begin with. Vital rate barcodes are specific to individuals, so there's no barcode for those fish. We're filling in through GRP width. Length is probably not a good one to fill in by, but for these purposes, we're just going to do this. Make sure you're filling in columns that make intuitive sense with your data. You don't want to fill in like a length or weight column really with this because those lengths and weights probably aren't associated with the data you made explicitly missing. But for these purposes, this is just showing go from site to the grip width column and fill in from dot direction equals down. So from top down, fill in that information. We save this as fish3. If we look through this data set, there are no missing rows now. There are no rows that are just NA completely throughout, which is exactly what we wanted. We wanted them filled in with the appropriate data, all the site information, all the field station information, the pools, the start date, the F date, everything there, stratums, DO, temperature, from the sites that they were collected from for the species that were originally missing. We still wanted that information. This is how you fill it in. Just think about which information makes sense here. how to arrange it so you can fill any of their top-down direction or bottom-up direction. And this would just be up if it was the other direction here instead of down. To do all these things in one chunk of code rather than here we completed it making an object and then we filled it in making a second object, just put the lines of code together. It does the same exact thing. This is just the complete code. Complete to make those catches 0, arrange your data, and then fill it in. Same exact code, just fill it in all in one chunk there. So this code makes the assumption that all species would have been ID'd to species and processed if they were encountered in all years of the time series. Because we just have 1 year, that's fine. However, it's not uncommon for monitoring programs or other surveys, things like that, to change how you ID or group species, like bait fish or forage fish versus the specific species ID. So really think about if you're using long-term data sets or something like that, if there have been changes in how the protocols or identification or anything like that has shifted across time. It's really important to know and like think about. And before you can do like a complete like that, then I would factor recode or collapse or just look at your data and figure out where can you make it congruent across time. And then we're going to talk about rounding next. So rounding is especially helpful when you're calculating summary statistics or when you're like saving your summary statistics from R or a table that you made, because R is just going to put however many decimal places it wants there, basically, and a lot of times they're really long. That's not something you want in a report or publication. It's distracting. You just want it to be simple, 1 or 2 decimal places or whatever your significant figures are there. There's a couple different ways to round values for calculated data. So this is a previous example we used using dplyr for rounding. So for example, let's say in our fish data set, we're grouping by species here because we want to get the mean, min, and max total length of every single one of our species. So when we calculate this, the min and max are fine here, but the mean total length that's calculated has a bunch of decimal places, 5 different decimal places. And that's not something we want to put in our report. Maybe we want to round it to the nearest whole number. Maybe we want to round it to the 10th place or to the tens place even to make it like a length bin, for example. So this we used before to round the mean. It's within you're calculating the mean within the summarize function. It's a function round, and it's the same thing here. So it's literally copying and pasting the mean length right here. So put your function and then whatever column you want, then comma and how many digits you want. So maybe we want 2 decimal places. Digits is the number of decimals. So this overall is the same exact code, except we're including the round function in digits equals 2. So we'll see what that is. So we have 2 decimals now because digits equals 2. You can change the number of digits to whatever significant figures are needed. So here digits equals 4. We would have 4 decimal places. But why are digits here, like positive number of digits associated with decimals? That's not as intuitive. Maybe like if I looked at this initially, I would have thought, oh, just the number of numbers there. So like not just the number of decimal points. To go the other way, if you want to round to like the tens place or whole integer or something, it's actually negative numbers for digits. So -1 here is going to round to the nearest tens. So 50, 110, 340, 60, etc. So play around with these decimals. Positive values are, or digits, positive values are decimals. So this is the tenth place, whereas negative one is the tens place. They are just doing different things on opposite sides of that decimal. So this is a way to get number of digits that you want here. You can also use things like floor and ceiling to round values down or up to the nearest whole number. Floor rounds everything down. So here we're going to look at just mean total length as a simple example. Again, we've got all these decimal points here. We're going to use floor, which is just use the wrapper floor instead of round on mean total length. That's the only thing we're changing here is just this wrapper argument or function floor. It rounds everything down to the nearest whole number. So this is 47 and a 4 here, so it's going to round down to 47. Same with this, should be 110, 342, 62. This is going to round down, so 227 instead of 228. Same with this, 139. Yep, 227, 139. So even though those were like 0.8, 0.9, it's rounding down because we're rounding down with floor. Ceiling does the exact opposite. It rounds up. So all of these numbers are going to round up to the next one. So it should be 48, 111, 343, 63, 228, 130, or 140 there. Yep. So 48, 111, everything I just said. And that's just the function ceiling. So ceiling, high up, floor, down, just rounding up or down to the nearest digit. These can be helpful when you want to round to length bins. So if you're rounding up or down to length bins, like if you have anything between like 50 and 59 and 0.9 is in the 50s, you can round down. How can you do that though? Is that because it rounds down to the nearest integer? Is you can do some like multiplication in here to say length times, let's do this, length times 10, and then outside of floor, you can do like divided by 10 or something like that. So let's see. Oh, that didn't do it. I did this other day, but now I'm blanking on it. Oops. Anyway, you can play around with this to get those length bins or anything that you do need by doing some like multiplication and stuff like that. And it'll help you get what you need for this. If you need specific length bins, this would be the easiest way to do it to round up or down and like multiply by the numbers and just like figure out what's going on there. Let's see if it does that. No, okay, I'm gonna give up on that. I can post the code or something later for that specifically, but I'm blinking on it in the top of my head when I did a length bin the other day. Okay, and then you can also combine floor and ceiling with other functions like round any in the plier package. So this is not dplyr, this is the plier package. It's before dplyr. These combined functions can be really helpful when creating length bins. So this is another way to make length bins. And this might be a lot easier to do than me trying to like finagle the like times 100 times 10 for those. Because it's doable that way too, but this is probably easiest. So load the plier package. We can round down to the nearest tens place, for example, for a length bin. So use our fish data set. We're just grouping here, saving as this object. We're grouping by species still. And we want to summarize again the mean total length. So all of this so far is the same code that we've been working with for rounding those values. Here we want to round down to get the nearest tens place to create some sort of length bin. So you can say round underscore any as the wrapper, and then it's still the mean length. This 10 here means round down to the nearest tens place, and f equals floor. So the function equals floor, we are rounding down. So easy length bin rounded down. So this was 47 point whatever, was 110 point whatever, etc. It's rounded down now to the nearest tens place. So if you were doing like 10 millimeter size classes, so it'd be an easy way to do it. Much easier than me trying to finagle the other thing. If you want to round up, it's literally the same code. So all of this is the same code. But now f function here equals ceiling. So this is going to round up tens place. So it's now 50, 120, 350, etc. Let's say we add another 0 in here for 100. It's rounding down to the nearest hundreds place, which is 0 for this first one because it was about 47. 10 or 100, I mean 300, 0, 200, and 100. So play around with these numbers if you do need length bins or anything like that. This is a straightforward way to do this, copy and paste and change it. So that's all for today's for data management. And then next time will be data management 2, which gets a little bit more into some of the other functions you can do to really wrangle that data and more finalize it before you start doing analyses.